exam, which is now pushed back a little bit, we will have chapters 6 through 9 on the exam. Chapter 6 is acids and bases. Believe it or not, we advance here, we're done with chapter 6. Okay. We've talked about everything that we're going to talk about with chapter 6 as far as acids and bases go. It's just a question now of practicing those rules. What are the definitions of an acid and a base? And then what do you evaluate based on? Okay, we've got those 6 codes behind it on what defines our acid-base reactions or what defines stability. You have to use those 6 codes. Okay? Just as a quick review, what are those 6 codes that we should be evaluating? Where do we start evaluation? Charge. Then we move to size, electronegativity, 4, resonance. Feel free to keep talking while I'm trying to frantically write everything down. 6, hybridization. It was kind of sarcasm, you could keep talking. Hybridization. And then there was that Mo brought up with picking hydrogens off of alkanes on hydrogens that aren't acidic. How would you rank them? I'm not even sure what to call that because that doesn't really fit under any of those categories. Maybe substitution. Substitution patterns, maybe. This is primary, secondary, tertiary. Whoops, not tertiary. Okay. Rule 6 rarely gets tested on. The only reason substitution patterns I'm putting in there is because Mo pointed that out. I don't think I would ever test on that, so I'm not throwing you under the bus there. Okay. But it could theoretically come up. Hybridization only comes up as an explicit question when you look at a structure, which one is more acidic. Okay. You've seen a version of that question already in your older exams. Most of the questions that you encounter sit in either resonance or usually rules 2, 3, 4 are usually where you're evaluating. Okay. Sometimes you'll see induction, sometimes you'll see charge, but for the most part, 2, 3, 4 is where you're going to be evaluating your stabilities. All of those come back to applying them to the definition. So when we look at an acid is a proton donor. To evaluate the strength of an acid, we look at the conjugate base. Okay. We want the weakest conjugate base for a strong acid. Why do we want a weak conjugate base for a strong acid? If HA is strong, what does that mean? The reaction occurs. It goes to the right. If it goes to the right, what does that necessarily mean about the products? The products must be stable. Since H plus is inherently going to be unstable as an acid anyway, I can't evaluate H plus. What I'm looking at is A minus being most stable. Okay. Believe it or not, this is just applying the definition of what an acid is. There's nothing fancy beyond this. We're just looking at the reaction and writing it out. We're drawing a picture to try and help us interpret the question. You should be doing this every single time. Okay. What happens if instead of asking about acid strength, I switch it up and say, well, I want to know the strongest base? Well, how does that change the question? Well, the base needs to accept a hydrogen to then become HB. So we could look again at the product and say, well, it must be the weakest acid. Okay. Which would mean the least acidic or the most stable acid. The problem with that, okay, is when we looked at our acids, did we rank them based on their acid characteristics? No, we ranked them based on their stability of the base. Why did we look at the base and not the original acid? Because the base has electrons. It's the electrons that we're trying to zero in on and look at the stability of those electrons. The more stable the electrons, the easier we can interpret. So when we look at base strength now, I don't want to evaluate the weak acid or the conjugate weak acid. What do I want to evaluate? I'm going to evaluate the base outright. That's where my electrons are. I'm not evaluating the stability of a product. I'm evaluating literally the base structure. Okay? Now in this case, if I want a strong base, what do I want the charge to be?
Negative.
Okay? I don't want neutral anymore. Neutral meant it was stable. It didn't react. When I'm looking at a strong base, the whole point of a strong base is to do what? Donate electrons. It's supposed to react, which means the charge now needs to be negatively charged. I need a larger negative charge. So I'm still evaluating charge, size, and electronegativity, but I'm flipping my logic on it. Instead of looking at the most stable, I want the least stable. Why? The definition has changed under which I'm applying those rules. Okay? So you have to know your original statement, and then you have to apply these rules back to whatever that statement is. If you just go through, well, I always want the most stable, that's where things are going to go wrong. Most students screw up labeling base strength because what they've done is memorized how to label acid strength, which is the complete opposite of a base. So of course it's going to get marked wrong. Okay? It takes practice of going through and evaluating each of those stages. We've done multiple kind of iterations within the acid strength. The base strength becomes a much larger issue in second semester. Okay? After that, we have Chapter 7. Chapter 7, you've already watched a video on. It talks about all the individual mechanistic steps. There's a question in Smart Work that asks about electron-rich and electron-poor. Okay, I think there's just one, but I'm starting to think there might be two. Okay? That question can be a bit tricky to deal with. That's why this slide is here, to summarize that as cleanly as possible. So that when you look at a structure and you're trying to label it as electron-rich, can you identify some characteristics between it? So number one, electron-rich is going to be an electron donor because it has electrons. Okay? You don't ask the homeless guy on the street for money because he probably doesn't have any. You ask the guy that has money for money because, well, he has it. Okay? The same thing's happening here, even though the guy on the street's probably going to help you more than the other guy. But that's a different topic. Okay? Because it has electrons, it's probably going to be negatively charged. It's probably based, shoot, I thought I was going to come up with LA first. Okay, LB, what is LB? Lewis base. BB, Bronsted base. N, nucleophile. Because all three of those substances are electron donors. Okay? So if you look at a structure like, oh, I know that's a Bronsted base, you now know it's electron-rich as well. Okay? It's just trying to give you something to key off of to help you classify. Okay? You're typically looking at atoms that are highly electronegative, like oxygen. Okay? These are typically hidden behind nonmetals. Okay? Because if I have a nonmetal, or sorry, I shouldn't have highlighted nonmetals, I meant to highlight metals. They're typically hidden behind metals. Why? What kind of bond do I have between a metal and a nonmetal? An ionic bond. Kind of like sodium bonded to chloride. And if that's an ionic bond, where do the electrons spend all of their time? On the chlorine. And I end up with a negatively charged chloride. Well, sodium, because I remember all my solubility rules from 151, is always soluble. So it's a spectator ion. Really all I'm concerned about is the chloride. Chloride has more electrons, negatively charged. It's highly electronegative. That is now an electron-rich atom. So by identifying some of these patterns and looking for them, it can help you identify these categories. Once you have the categories, you can then start to say, how do they react? Okay? Well, how would they react? If I have an electron-rich atom, what is it going to try and find? An electron poor. So if I have a negative, the negative is going to try and find a positive. So when you look at a structure, what you need to be finding are negatives and positives. In first semester, there's typically only one negative and one positive. In second semester, you'll get 4 or 5 negatives and 4 or 5 positives. Okay? which means you have to go through and evaluate which one is more positive or more negative. How? Number one, charge, size, electronegativity, resonance, induction. You have to go back to those same rules and establish which one's going to dictate out. Okay? The last thing in Chapter 7 I want to talk about is this concept of the Keto-Enol tautomer. Okay? It's another kind of fancy intermediate. It plays kind of a surprise gotcha trick in first semester. If you have to move into biochemistry or anything to do with biology, this is the chemistry that dictates virtually why we exist. Okay, is the Keto-Enol tautomer. That's a bit overstated. I apologize, but not that far overstated. Okay, if you look at carbohydrate chemistry, virtually every single reaction run through carbohydrates does some kind of Keto-Enol tautomerization. Okay, so what are we talking about here? If we go through and take a look at the structures shown on the left, those two structures are resonance structures of each other. Okay, we have a negative charge on that oxygen. We can move the electrons down, which would move the electrons onto the carbon. That would generate the bottom structure, or I could take those electrons and move them back up. Okay, so they are resonance contributors. Okay, they are both negatively charged, which is good because they're resonance structures. Okay, so we have two basic sites. If I react these with an acid, I would expect the hydrogen to react with one of those negative positions. If I did that, I'm going to get different results. Okay? The structure that I would draw out of this would look like a carbonyl where the hydrogen went to the carbon or the hydrogen went to the oxygen. Okay? And as we can see in this slide, already they're saying it doesn't go to the oxygen, it only goes to the carbon. Why would it go to the carbon and not the oxygen? The electronegativity of what? If we look at carbon versus oxygen, which one is the stronger base?
Oxygen.
Carbon is the stronger base because it is less electronegative than oxygen, which means that negative is going to react with our hydrogen. Okay? And we end up with the keto form and not the other form, which they call an enol, which tends to trip people up. Okay? For those people that may have been tripped up by that, let's go through and take a look at that structure without the big X across it. What is the name of the functional group in red?
Alkene.
That is an alkene, named as an ene, right? What is the functional group in purple?
Alcohol.
An alcohol, named as an ol. What do I now have?
Enol.
An enol. It's the combination of those two functional groups. Okay? So there was a logic behind the name. You may not have recognized it, but that's where it's coming from. Okay? The keto-enol tautomerization is now how do we oscillate back and forth between the enol form and the keto form. Okay? That's what we're talking about when we talk about the keto-enol tautomerization. What's the relationship between the enol and the keto form? Are they resonance structures? No. Why? What happened to the hydrogen? It was removed from the oxygen and it was then placed on the carbon. I've broken a sigma bond, so they aren't resonance structures. Okay? However, if I look at a keto compound, some of it will naturally form the enol state. It is always present. And it's present in a high enough concentration that it does dictate some of the chemistry of that carbonyl functional group. So it is important enough that I have to acknowledge its existence, but not quite important enough that I would draw it as the enol form. Okay? So all we're trying to do is acknowledge that it's important, that we have to evaluate it, and we have to remember that it's there. Okay? Why do we expect the keto form more than the enol form? It really comes down to bond energies. And if you go through and look at the bond energy for the red one, we come in at 1477 versus 1430. Okay? That 1477 is a slightly more stable system than in the 1430. That means we favor the red one. Okay? I don't trust numbers, which is a bit silly because numbers typically lie less than humans. Okay? We could look at some kind of hand-wavy arguments behind this. What is the hybridization of the oxygen and carbon in each of those structures? Let's take a look at the blue one. Our carbon is what hybridization? sp2. The oxygen? sp3. Carbon? sp3. Oxygen? sp2. Okay? So we could potentially say we have a hybridization effect. Okay? The less hybridized we are, the more electronegative. Which element is more electronegative, carbon or oxygen? Which one wants to be less hybridized? Oxygen, because it's less electronegative. sp2 versus sp3. Okay? It's an important relationship for those of you doing smart work. There's lots of acid-base questions centered on the keto-enol tautomerization, okay, because it is an important relationship. For those of you that don't have to take second semester OChem, you never see this relationship unless it's explicitly shown to you. So if you can jump straight from first semester OChem into biochem, and you're like, where's all this chemistry coming from in biochem? It's all coming from second semester OChem, which for some unknown reason they decided to remove from the requirements. Okay? You at least now have a context of where it's coming from. Remember, it will show up this semester at the very end in those last, like, 2 weeks. Okay? We're going to see a reaction that is going to surprisingly generate a ketone instead of doing some other chemistry. Okay? So, 6, 7, and 8 back to life. We looked at this reaction, okay, this sequence. Because we're already behind, I'm not going to make you do it as a quiz. We could go through and add curved arrows. In our first step, our oxygen attacks the hydrogen. Second step, our oxygen steals the electrons. We get the rearrangement. Then we get the bromide nucleophilic attack. If we went through and labeled our mechanistic steps, we have our coordination. We have a rearrangement. That says rearrangement. We have a heterolysis. And then we have acid-base. Altogether, the reaction that's happened here is a substitution. Okay? So this now includes pretty much everything we've talked about up to this point. 6 and 7 are now all covered in that single system. We've got all the curved arrows in there. We've got the mechanistic steps labeled. We have the overall reaction labeled. Okay. What 8 brings in now is it starts to say, well, now that we understand something about what those things are, what is the energetics behind it? Remember I said we were going to deal with energy diagrams. So let's do an energy diagram for this reaction. Okay. If we started off, we don't know the exact values. So we're going to pick our reactants on the far left, and we're just going to say somewhere in the middle. So there's my reactants. For that first step, what do you think is going to happen? Is that first product, we want to call it A, B, C, D, or 1, 2, 3, 4? 1, 2, 3, 4. So we've got 1, 2, 3, and 4. Where is 1 relative to our reactant? What do you think, higher or lower in energy? So I've heard lower and I've heard higher. For those of you saying lower, why do you say it's lower in energy? What's that? Okay, we can work with that. For those people that said higher, They said that 1 is higher in energy than the reactant because 1 has charge. That's a good place to start. Okay? We have charge in our structure, which is going to suggest that that structure is higher in energy. So there's 1. Higher in energy than our reactant. Where is 2? To the left of 1. I mean right of 1. Right of 1. Is it higher or lower in energy than 1? Why is it lower in energy? So we're going to get some interesting answers here. We could say lower because carbon is less electronegative than the oxygen. I would kind of agree with that statement. We're probably going to run into an issue with that. What's that issue?
It's lower because it's tertiary carbons. The carbon's more
Octets. The carbon doesn't have its octet. The oxygen does. So we run into some kind of gray area there. I would make the argument that what you started with, Morgan, makes sense. Okay? That 2 is probably a little bit lower, but I'm going to make the argument it's not much lower. It's not much lower because we have something going against it. It has that octet issue. Okay? What about 3? Three is now higher than 2. Why is 3 higher than 2? What's the difference between them?
3 is a more stable carbocation.
If it is more stable, is it higher in energy or lower?
Lower.
3 has a tertiary carbocation. 2 has a secondary carbocation. That makes 3 more stable, which makes it lower in energy than 2. Should it be lower in energy than our reactant?
No.
Why not? Still has a charge. Where's 4? Lower than?
It's lower than 3 but
Lower than 3.
than reaction.
Okay, so everybody agree that it's lower than 3. Why? Charge. Lower than the reactant? That one becomes a little bit trickier to deal with. They're both neutral, so that's going to be hard to evaluate. Okay? Most of our reactions to actually proceed need to be slightly exothermic. So you'll note I have a slight bend on that, being a little bit under. If we went through to draw our then activation energies, whoa, overjumped that one. Would be probably somewhere along those lines. Okay? Dictating exactly where 4 is with respect to the reactant, I'm not concerned about yet. Okay? The reason why I'm not concerned about it is that we don't see anything particularly energetic there. What do we need to evaluate if not the organic structure? Was there something else produced? Water was also produced in this reaction. What was the other reactant? HBr versus H2O. If we factor those two compounds into our analysis, that's now going to change some of our interpretations along the way. Okay? Where I would like you to keep focus is in with the organic structures. Don't worry so much about the inorganic structures. So when we look at some energy diagrams where we see things that are kind of counterintuitive, okay, usually what's happening is we're factoring in all of the other materials, like water and HBr. Okay? Because that can get extra tricky to interpret. Stick with the organic structures. That's where I expect you to sit. Make sense? Okay. So chapter 8 is really now about the energetics. How do these reactions occur? What are the energy diagrams looking like for each of these? What does that mean about the relative speed for a reaction? Where's slow steps? Where's fast steps? Okay? all of that fun stuff that you wish you had forgotten from 152. Okay? Or that you actually got granted and you forgot from 152. Okay? So what we're looking at in Chapter 8 is a lot about kinetics and mechanisms and rate laws and all that fun stuff. Okay? So, our overall reactions, acids and bases, was Chapter 6. Chapter 8 and Chapter 9 are looking at substitution and elimination. The end of the semester is going to be our addition. Okay? Substitution and elimination is what we're doing in 8 and 9. 8 is pretty much saying, this is substitution, do it. This is elimination, do it. This is an SN1 substitution, do it. This is an E2 elimination, do it. Chapter 9 is, here's this reaction, I don't know what it is, you tell me. So you have to take all of the rules that you've learned in Chapter 8 and apply them now to a new system where you have to be able to predict those reactions. Okay? So, general patterns, acids and bases, just the transfer of hydrogen. Substitution, we're an exchange of an atom other than hydrogen. Elimination is a removal of a small molecule, so it's breaking of 2 sigma bonds from a structure that results in the formation of a pi bond. Okay? If you see a pi bond, think elimination at this stage. Okay? What happens if you see a pi bond in the reactant? Now you should be thinking addition. Okay? Radicals just go all squirrely, so don't worry about it right now. So, our reactivity of our alkyl halides. There's a lot of information up on this. Okay, we've got both substitution and elimination listed out here. You'll notice that we see these E1s and E2s, SN1s and SN2s. What those are representing are the individual types of mechanisms that can happen in a substitution reaction or in an elimination reaction. After that, we see summaries talking about rates. Rate equals rate constant times the concentration of a species. Okay? That would be the rate law for the E1 reaction. Okay? Substrate. Notice we're saying tertiary is greater than secondary. Well, that 3 circle is our tertiary structures, like tertiary halides, tertiary carbocations, react faster than secondary. Base strength. I want weak bases. Typically, I want to see heat. Solvents. And I should actually just cross solvents out for the elimination. Okay, so this summarizes all of those intricate pieces. Okay? So if we take a step back, take a look at our substitution and elimination general forms of our reactions. What do you see within those general forms? So look at the pictures. Anybody notice anything that looks odd? What element is Lg? It's a leaving group. Okay. What element is nuke? It's a nucleophile. What element is solvent? It's the solvent. Okay. It's whatever was there to dissolve. So what we're looking at with those colored things is highlighting the extra pieces that then get evaluated in the following slide. We end up looking at the solvents, the nucleophiles. How do those pieces of our original structures affect what mechanism we look at or how it occurs? Okay? So what we have here is just the big, horrible summary of everything. Okay? Why show you the horrible summary now? Because usually at least one person a semester says, I wanted the horrible summary first. So this is for you. Okay? Continuing with our horrible summary. Each of the mechanisms has some kind of complication associated with it. Okay? SN1, loss of stereochemistry, meaning Chapter 5, where we had to deal with chirality. This is where it shows up. We end up with racemic mixtures. Okay? Another complication. If I have an SN1 mechanism, it runs simultaneous to an E1. So if I think I'm doing an SN1, I'm also doing an E1. Okay? SN2, what happens? Inversion of stereochemistry. If I start R, I go S. If I start S, I go R. So do I have to know those concepts from chapter 5? Yes. Okay? They stack and apply in. In elimination, we see some reference to trans. Okay? Anti-alignment for E2. Anti-alignment is really coming from Newman projections. So I have to know what my structures look like to be able to come up with interpretations or complications from each of these mechanisms. Okay? It builds. We have to be aware of these. Okay? And then, of course, we throw in some extra words just because why not? Zaitsev or Hoffman. When we talk about those, you'll see my complete and utter disdain for those. Okay? Those are people's names. I don't hate the people. I hate that we're naming things after them. Okay? Because they did some cool stuff. Okay? But we end up naming or associating their names with those reactions because they dictate something about the products. Okay? So, that was our summary. Let's look at a general substitution. Okay? Every reaction, what you want to evaluate is what things changed. Okay? And in our what things changed, what bonds were broken, what bonds were made. So in theory, you've all had now a second to look at it. What bond was broken in this reaction? Carbon iodide bond was broken. What bond was formed?
Carbon chloride.
The carbon chloride bond. What else happened?
Carbon attached to it became positive.
Do you see a positive carbon anywhere in there?
No.
No. So I know where you're going, but we aren't there yet. Okay? That's it. In this reaction, two things happened. That's it. Okay? Scientists did the same thing. When we originally started looking at these, we just said, what happened? Oh, only two things happened. The next fun question becomes, how did those two things happen? Or really, when did they happen? And it turns out there are three possible ways that those two things could happen. What are those three possible ways? Okay. One way I heard somebody mumble, chlorine comes first. So chlorine bonds. Then what would happen? Then iodine leaves. Or iodine, I'm just going to say breaks. So chlorine bonds, then iodine breaks. What else could happen? Okay. I could have the chlorine bond, same time, iodine leaves. Or iodine breaks. That is different than the last one we listed. The bottom one says the chlorine forms a bond. Once the bond has formed, then a bond can break. Step 2 says it all happens at the exact same time. Those are two distinctly different things.
So the number one would be the chlorine iodide bond needs to be broken, and then
Iodine breaks,
then chlorine forms.
then chlorine forms. Really? That's it?
Yep.
So when we talk about substitution reactions, there's only three possibilities. Well, that's not that bad.
It's two.
This reaction.
Two possibilities.
There's only two possibilities. Why are there only two possibilities? I've got three things.
3 breaks in the octet.
Can chlorine bond, then iodine break?
No.
Okay. Mechanistically, what are we saying is happening there? Saying this chloride comes in, forms a bond. What would the result be of that single arrow pushing? There's the iodine, there's the chlorine, there's that R. Why is that a problem? I only see 4 bonds. You mean I also have to remember that there's an implied hydrogen initially in that structure? back all the way in Unit 1 where I said we have to watch out for implied hydrogens? Yeah, sorry, we do. We have exceeded the octet. Okay. So I cannot form the bond first. So really when I look at substitution, there are only two possibilities. There's not a third. Okay. So we either break the bond, then form a bond, or we do it all at the same time. That's it. So when we talk about substitution, that is all that is happening. Everything that we discussed on those previous two slides, the complications, what things we should be evaluating, all come from just looking at those systems happening in that sequence. Okay? Because I don't remember what's on the next slide, and I kind of want to go through at least one of those. Yeah, because the next one looks at elimination. And I did not want to erase all of that. Let's try that again. Let's look at the first one. What would our mechanism be? So we want to describe what you see there. What does it say to do? Break the iodine bond. So if we go back to my reactants, all I'm going to do is take the electrons in that carbon-iodine bond, and I'm going to put them on the iodine. Why would I put them on the iodine?
It's easier for iodine to accommodate the negative charge to the sides.
So we got lots of answers that got floated out there. And if we don't know, what we could do is look at the two possibilities. We could have the result where I have this, or and I'm just going to draw I positive. Those are the two possibilities in breaking that bond. They either went with the iodine, bottom result, or they went with the carbon, top result. Why would they favor going with the iodine, not the carbon? You mean we need to evaluate something about the stability of those products using charge? Is there a difference in charge?
Yes.
Carbon's negative, iodine's negative. Is there a difference in charge?
No, not charge.
No.
Side.
Charge does not impact this. What's the next rule? Size. Is there a difference in size between iodine and carbon? Yes. What does that difference dictate? Iodide is more stable, which means iodide takes the electrons. Okay. This isn't just an arbitrary system where we just throw things out and just break them around. There was a reason behind it. That's why we had those rules. Use those rules every single time. Right? We broke the bond. Then what happens? Literally, I think it says right after, iodine breaks, then chloride forms. Why would chloride share its electrons with the iodine, the carbon as shown? One is negative and one is positive. What are we trying to do? Neutralize the charge. That's the whole point of this. Okay? The result being, I get the chloride attached. Everybody agree? Cool. Let's do some fixes here. Instead of that being an R, I'm just going to make it a methyl. And by making it a methyl, all I have to do is erase the R, right? Okay. So let's talk about some of the things that were on the previous slides. Okay. There was something about complications, right? Because everybody loves talking about chirality first. Let's start there. Okay. Do I have a chiral molecule to start with? Yes, there is a chiral center there. Do I have a chiral molecule at the end? Yes, so I have to be concerned about it. On that previous slide where I said the complications for the SN1, we don't even know this is SN1 yet. It is. I didn't just write one randomly. That was thought out. Okay. It says we need to be concerned about chirality. And what did it say? We had loss of stereochemistry. Okay? Loss is in quotes because it says we end up with a racemic mixture. So we don't lose stereochemistry. It's still present here. But I get two products. Okay? I would get one where the chlorine was wedged and one where the chlorine was dashed. I get two products. Okay. Why would I get two products? Something about this mechanism actually tells me that there are two products. Really? Yeah, I just drew the two products. That was a joke. Ha. Something else about the reaction tells me I need two products. When I look at those two products, why do I know they're different? How do I know there's a stereocenter?
In the original structure, in that structure, there's a carbon that's bonded to four different
things. The carbons were the same though, right? What is the thing that causes this to be a stereocenter? The chlorine. Okay. When did the chlorine come in? At the end. What did the chlorine react with? A positive charge. So the result of there being two products is happening in this last step. Why does this last step tell me there are two products? What is that negative charge reacting with? A positive charge, okay, which would be an sp2 carbon. Where is the positive charge held on that sp2 carbon? In a p orbital. The positive charge means there are no electrons there, which means it's an unhybridized p orbital. What do we know about the shape of the p orbital from Unit 1? It's a dumbbell, meaning it has two lobes, one above the molecule and one below the molecule. Both of those lobes have no electrons in them. Where can the chloride attack? The top or the bottom. There is no preference, which means two products. The mechanism tells me I have two products. Okay? It requires that I interpret every nitpicking detail of my structures beforehand. Okay? This is where mechanisms are awesome. They can give you that content. Okay? For those students that are like, or heard there's tons of memorization, this is why they had tons of memorization. They didn't remember each of these pieces of content, and what did they do instead? Those previous two slides, they memorized all of that content. The mechanism tells us every nitpicking detail of what you're told to memorize. You have to be able to do that interpretation. That takes practice and work all the way through this, and that takes ultimately time. Okay? If you can't do all the practice and work, start working on the memorization right now. That's why those big summaries are there. Okay? Kind of makes sense? Okay. One of the other things on that previous slide said something about substrate. And if we looked all the way back, there was no reference to substrate anywhere else. In our reaction, the substrate is what we're starting with. This is the substrate. For an SN1 reaction, what do I want my substrate to be? Well, the memorization said tertiary reacted faster than secondary, faster than primary. Why? When I look at this reaction, there's two steps. Which of those two steps is the most important to this reaction happening? If you think about how you got here this morning, which of those steps is the most important to you actually getting here? Waking up? Really? You don't wake up other parts of the day and don't make it to class? Like on Saturday, you just never wake up? Tuesday, Thursday, Friday?
Pretty much.
You just never wake up. The only thing that dictates whether you get here is that you wake up.
No.
No. What dictates that you get here?
Getting into the car and actually driving here.
Driving to the class. That's what dictates that you get here. Waking up, yes, you need to do that. That is an important step. Okay? And yes, that is your first step, but that doesn't dictate you get here. Okay? What could help you get here faster? Okay, waking up could be part of that. Okay, but if it takes you an hour to drive here, what if you could shorten the amount of time in that drive? Instead of driving an average of 50 miles an hour, you drive 70 miles an hour.
You're driving faster.
Okay? That would get you here with a significant change in your time. Okay? What if you don't brush your teeth?
Maybe even a little bit faster.
A little bit faster. How much time is that going to help?
Not very much.
Not very much. Okay, so what we're looking for is the rate determining step, the slowest step in your reaction. That's going to be the one that dictates all the important stuff, okay, or a lot of the important stuff. This reaction becomes tricky because there are two steps. So which of those steps is the slow step? Why is the first step the slow step? I start neutral and I become charged. I'm missing an octet. Is that a good thing? No. Is that an easy step to happen? No. Okay. Missing an octet to becoming octet satisfied and neutral. Is that going to be an easy thing to do?
Yes.
Yeah. Which of those steps is the hard step? The first one. Okay. When I look at that first step, what I'm concerned about is just that iodide breaking off. Why would the iodide break off? Well, why did we say the carbon didn't break off?
Because it's already by itself.
The iodide could stabilize the negative charge better. But what happens if I change the substrate? Now instead of it being a methyl there, I get rid of that carbon altogether. I still have the iodide. Is this going to change my reaction? Okay. Yeah? Why? The carbocation is also a contributing factor to my stability for this reaction occurring. And now when I look at this, I now have a primary carbocation. Are primary carbocations as stable as secondary? No. Which means that product or that intermediate is now higher in energy, which means it's harder to form. So when I think about my substrate, I want a substrate that's going to stabilize the carbocation as best as possible, which means I have to remember that my tertiary carbocations are more stable than my secondary, more stable than my primary, which means tertiary will react faster than the secondary, faster than the primary, under these conditions. Again, the mechanism gives me that information. Right? We literally haven't changed slides. We're looking at the exact same content. It's interpreting the information that we have. Okay? Kind of makes sense? So everything that we get, and just to give you an idea, we are going to change slides here. All of this stuff up here, looking at our rates, our substitution, nucleophile solvent, all of that information is derived by looking at our mechanism and thinking about what changed in that process. Does the mechanism, coming up with a mechanism, mean that it is true? Theoretically, I can get to campus in 5 minutes if I develop light speed. Okay. That is now a mechanism for me to get here. In 5 minutes, I can do it. I get up, I just move like light speed, shower, brush teeth, eat, shave. I don't shave, but whatever. Okay. And then get here. 5 minutes. Boof. Is that a likely thing for me to do?
No.
No. So what dictates that a mechanism is actually something that we should be studying? Is it true? How do we know it's true? I watched you, Mike. You don't have light speed. We do the exact same thing with OChem. We do it in lab. We test it in lab and we see, is it true? Right? The mechanisms that you are being asked to study and memorize and understand and apply have all been tested in lab. Right? And more than likely what happened is they were tested in lab first, then somebody went back through and said, oh, I saw something different. So I'm going to now report what I saw. You don't get the benefit of that. What you have to do instead is just analyze all their results. Okay, so you get a lot more of the theory, but none of the lab. That does kind of suck for you, but you also only live at most 100 years, and most of this content was like 200-300 years. So I'm pretty sure you don't have enough time to learn all that and then do whatever you wanted to do with the rest of your life. Okay? So, elimination. Right? What changes now? What is different about the elimination reaction in comparison to the substitution reaction? So I see a double bond forming in the product. What else is different? Kind of like ignore the man behind the curtain, ignore the little box. What else is different about the elimination? Okay, we can get into that. I would say it's even easier than that. So let's make the hint a little bit more less subtle. Well, ignore that. Substitution, we started with two things. Elimination, we can do it with one. Right? So we're changing how we're evaluating what's happening. We're looking for those subtle cues that key off that something is different about it. Okay? So yes, one was the formation of the pi bond. That's probably the most obvious, okay, and probably the best one to evaluate. Okay? But after that, we really only need one thing, and that one thing becomes two. Okay? It's not perfect, and we'll see why it's not perfect in a second. So what things changed? Okay? The X bond broke. What else happened? Pi bond formed. And a hydrogen broke. This is now becoming more complicated, right? Instead of there being two things that changed, we now have three. I'm going to make the argument we only have two things. What are those only two things? Two sigma bonds breaking and a pi bond forming is still three things. You're just combining them as one step. They're not steps. There's still three things happening. Here's a hint. What does that hint tell you? Yeah, there's resonance. What if instead of drawing it as we had there, we did this? What things changed? I broke the hydrogen. I broke the carbon chlorine. And that's it. Those are the only two things that happen in an elimination reaction. Okay? Those two things result in an unstable structure that immediately stabilizes by making a pi bond. Okay? But the pi bond is not our limiter here. The limiter is dealing with our hydrogen and our leaving group, that X. So we're really only breaking two bonds, which then comes back to another question. Well, what is the order that those two things break? Okay? And again, we should be focusing on ending with that pi bond. What happens if I break the X bond first? Where would those electrons need to go? Making a pi bond. Is that a problem? Let's draw the result. I have an octet problem. Can I break the hydrogen first? No. Okay. So what has to happen first? I have to break the leaving group off first. Okay. Because we already did one where we did the leaving group first, let's go ahead and switch this one up, and instead we'll have the leaving group leave and we'll remove the hydrogen at the same time. Okay. Now they're both happening at the same time. What is the result of that arrow pushing? It's exactly what's shown. It happens in one step. I get the answer right out of the gate. There it is. Okay. Complications behind what we're seeing here. Okay. X is leaving with electrons. These are electrons coming in. Because those are both electrons, those need to be on opposite sides of the structure from each other. You mean the hydrogen and the X must be on opposite sides of the structure? Yes. If they were on opposite sides of the structure, what would their alignment be? Anti. There's the anti-alignment in the E2 mechanism. Okay. Why do we call it E2? Okay. Versus the other one we had SN1. That has to come down to the reagents used. Okay. I have to break that hydrogen off. Is that an easy bond to break? Okay. A couple people said no. Why not? The difference in electronegativity between carbon and hydrogen is almost identical, which means that bond ain't breaking for its life. The carbon-X bond, that's easy, because X can stabilize the negative charge. Carbon can't stabilize that negative charge. We're kicking off H+. That's not a good thing to do. So I need something to remove that hydrogen. Okay. That hydrogen is getting removed with what? Okay, what would it, it's not leaving, what would it disappear from the structure as? So H+, meaning that species is acting as an acid. What might be a useful thing to react with that acid? A base. In this mechanism, I need to have a base present to react with that hydrogen. Why do we call this an E2? Well, this comes back to our rates. Okay? A rate law is rate equals K. Describe the K. No, I lied. Lowercase k, rate constant. What? Rate equals K times.
Are we doing, wait, is it an SN1 or SN2?
This is not SN at all. This is elimination, and it's E2.
E2? So that'd be the alkyl halide times the nucleophile. Cannot say correctly.
If we take a look at what's happening here, our rate in general, what is our rate law always dependent on? The slow step, how many steps do we have here? 1. So I'm okay, we're at the slow step, there it is. What else is it dependent on within the slow step? We actually don't care about the formation of products in most rate law conditions. We care about the concentration of the reactants. What are the reactants in this rate law or in this reaction? Well, we have a base and we have that carbon halide structure, which I'm not going to draw the rest of. How many species are in my rate law? 2. That would be known as what kind of order? Second order, also known as bimolecular. This is an elimination mechanism of the type 2. The 2 representing bimolecular. It has to do with the order from the rate law of the reaction. Okay? So the 1s and the 2s, both in substitution and elimination, all go back to rate law stuff. Okay? So we have to remember that from 152. Or we memorize some more stuff. Okay? So that's why this one's a 2, because we need that secondary base. Why did I not show the base outright? Because the other version of the mechanism doesn't need a base to remove the hydrogen. Okay? So it all comes down to what conditions you're running under. So we have to be concerned about what bonds were broken, what bonds were formed, and then apply all the rules that we've put together so far. Okay? There are all our options. So we went through and just looked at the E2 mechanism. Okay? So our process is going back to Chapter 7 and then stacking in all of those different mechanistic steps that you watched in that video. Okay? That not all of you have watched in that video, that you should watch in that video. Okay? So that you can apply them. I will explicitly ask questions. Here's a mechanism. What is the mechanistic step? If you can't tell me, you lose points. Okay? So, the simultaneous are elementary SN2 and E2. Okay? Both of these are trying to set that up. If we take a look at the SN2, or first off, which of these is substitution, which is elimination? Why is the top one substitution? So we could probably go with because you substituted. Okay? I would make the argument the bottom one was probably the elimination, and since you only gave me 2 options, I know the top one's substitution if the bottom one's elimination. Why do I know the bottom one's an elimination? There's the formation of the pi bond. Okay? So it's again looking for those pieces, trying to key off on something. Okay? What is our mechanism for the substitution? Well, here we're saying SN2. Okay? In the SN2, we're doing everything at the same time. Bond cleavage, bond formation happens simultaneously. That means that iodine must come in and attack to form the bond to the carbon at the same time as the bromine leaves. Bond formation and bond breaking have to happen at the same time for the elimination. Okay? In the elimination, the base must come in, remove the hydrogen, and form the pi bond at the same time. But then I would exceed the octet. So what else has to happen in the elimination? Also have to break the leaving group. Okay? So it's recognizing each of those pieces, adding the curved arrows, and labeling as we've discussed what the words mean. Make sense? Yes?
So you're saying that's always that one cleavage and one formation happens simultaneously?
SN2 and E2 are always bond formation and bond cleavage at the same time. Okay? They have to. If we go through and evaluate the 2 again behind these, what is the slow step for that first reaction, for the substitution? Which step is the slow step? There is no slow step in the first one? There's one step, which means the slow step is that one step. Okay? How many things are in, or how many reactants are in that? I have the iodide, and I have that carbon bromide. There are 2 things. There's the SN2. It's a substitution. 2 things in my rate law. We look at the elimination. Which step is the slow step? There's only one step. Rate equals the rate constant times the concentration of my base times the concentration of whatever that leaving group thing was. Again, 2 things in it. That's why it's a 2-type mechanism. Yeah?
So when you ask us, like, what is the slow step, or what is the step, are you looking for the rate law?
Eventually, that's where it would go, yes. So what I'm trying to do when I ask that question is first identify what the slow step is. We can't look at a rate law if you don't know the slow step. Your slow step always dictates your rate, always. Right? So your first step is to identify which is the slow step. If there's only one step, now things are easy. You just look at that one step. It'll be rate times your rate constant times the concentration of whatever reactants are involved in that mechanistic step. And the involved is an important word because sometimes you could draw a reactant but not have it do anything. Just because you drew it doesn't mean it's doing something. You have to have curved arrows showing it's doing something. Make sense? Okay. The stepped mechanism, SN1 and E1, both of them start with heterolysis. We break the bond first, then we follow that up. We either follow that up with a coordination, in which case we're doing a substitution, or we follow it up with what Carty calls an electrophile elimination. Okay? The elimination is a key off that we're forming a pi bond. The electrophile hint of that is that we're kicking off a positively charged species. Okay? Because it is positively charged, it can be classified as an electrophile. Okay? Heterolysis will generate high energy intermediates. Intermediates become questionable because what do those high energy intermediates want to immediately do? Stabilize. That stabilization does not necessarily mean complete the reaction you want. It may mean do something else entirely different that stabilizes faster. Okay? So anytime you have an intermediate, you have to be a little bit more careful when you go through and look at your mechanism. Okay? All we're trying to do is neutralize that reactivity. So if we look at the first step, the leaving group leaves. The result, we have the positive charge, and then we'd have the iodide. This is a perfect case that we could ask back to your question. I'm going to say the first step is the slow step, which it is. How many reactants are in that first slow step? Whoops, rates. Just ignore the S. Rate equals K times. But a bunch of people said 2. The chloride is also present. Did it do anything? No. Just because you draw it there doesn't mean it should show up in your rate law. Just because I'm good at these. Just because I draw a pineapple doesn't mean the pineapple should show up in your rate law. It's completely irrelevant. It has to be involved in your mechanism. Don't make fun of my pineapple. That's a solid pineapple.
It's a beautiful pineapple.
That was in less than 5 seconds. I challenge you to do better. Okay? We follow that up. So that was a heterolysis. All we did was break a bond. What happens in that next step? We'll call it blue to the left. What did we do? You formed a bond. So we did a coordination. Nothing else happened. It was just the formation of the bond between the chloride and our cation. What happens in the, let's call it the orange step? We broke off the hydrogen to form the pi bond. What came through and broke that hydrogen off? Okay, we could go through and say a base. But remember I said with the E1, I didn't need a base. Is that hydrogen actually pretty acidic right now? Its acidity is actually skyrocketed. Why is it skyrocketed? There's a positive charge right next door. If I remove that hydrogen, I can stabilize the negative on the carbon by doing resonance with that positive charge to generate the alkene. Right? So because the leafing group has left, my hydrogen acidity has now changed significantly. Okay? Probably not that significant, so we tend to add something else. We could add a base, but the other thing that we typically add for the elimination reactions to help break that bond. If I gave you a block of wood and told you to break it, how could you break it? with your hand. Okay, I say you can't use, but the block of wood is like 5 by 5. Can't use an axe. Can't throw it. How do you break it?
Drop it in a bigger wooden box on it.
Nope, can't do that. What? Someone actually, I think, said it.
You said heat.
What if you lit it on fire? Did you break it?
Oh, I said that.
You broke every single molecular bond within the wood. Yes, you broke it with fire. What can we do to break this? You can add heat. Heat's going to cause that carbon-hydrogen bond to vibrate. If it vibrates enough, it vibrates so far away that the bond breaks. Okay? So eliminations we can typically see with heat because we're trying to break not an easy bond to break. So heat can be something that we can add to help speed that along. Okay? So after that, do we care what the mechanism is? Okay? And everyone goes, no, yeah. Nonsense, yeah we do. Philosophically, yes. Okay? We always care about what happens because we want to understand the world better. Okay? But chemically, is it really that important? Okay, well, let's take a look at the results. If the leaving group leaves, and we generate this, we get one product. If we get this, we get one product. If we do this, we get one product. This, we get one product. Okay? Do I care whether I do a substitution or elimination reaction? Yes. Why? They're different products. That's a pretty significant difference. Yeah, that's chemically pretty important. Do I care between substitution? Yes. Why do I care? That's a chiral atom. With the SN1 mechanism, I get 2 products. With the SN2, I get 1 product. If you're going to try and get a high yield, do you want to do a reaction that only generates half of your potential target or all of your potential target? Okay? So chemically, it is a really big deal to know what mechanism you're working with. Okay? The last thing that I'll end on, I promise, is just a hint from what Cardi puts out. Okay? I've got a slightly modified version that takes into account all of those different pieces. So when you're thinking about your reactions, think about each of those pieces and what mechanism best wants that thing. Okay? So we'll look at that in more detail, I promise, later, but we got to be done now.